In this video, we'll work through a model of a market of network externalities. We will start by deriving the demand curve, then we'll introduce supply, then we'll look at the equilibrium in the market, we'll look at the dynamics in the market, and then we'll apply the model to the market of fax machines. After this, we'll also look at some implications of the model. So let's derive the demand. Consider the market for some good. Consumers are uniformly distributed along a line of length 1, and the total number of consumers is 1. The location of a consumer represents their willingness to pay. Before we look at the market with externalities, we'll find the demand in the market without network externalities. In this market, V is what they are willing to pay. So a consumer will buy the good so long as their willingness to pay V is at least as large as the price. This means that the indifferent consumer, the consumer with valuation V bar, is the one where their valuation is equal to P. So the indifferent consumer is P. Everyone to the left of V bar will choose not to buy, everyone to the right of V bar will choose to buy, and so the number of consumers that buy, N, will be equal to 1 minus the indifferent consumer, which is 1 minus P. So this 1 minus P is actually the demand function. It tells us how many units will be sold when the price is P. So let's draw this demand function. When the price is 0, the demand is 1. When the price is 1, the demand is 0. For prices above 1, the demand is 0 as well. For prices between 0 and 1, we have a straight line. So this red line is our demand curve. The equation of the demand curve is N equals 1 minus P. So just as usual, the height of the demand curve represents the willingness to pay of the indifferent consumer. So this is the market without externalities. Now let's introduce externalities. Now the consumer values the good at N times V. So the multiplication by N is how we capture the dependence of the willingness to pay on the number of consumers who buy. Now when the consumer chooses whether to buy or not, they don't actually know N, but in equilibrium we assume that the expectations of the consumers for the number of consumers that buy are equal to the actual number that buy. This is a consistency requirement. So now, consumers will buy as long as N times V is at least as large as the price P. So what does this do to the demand function? Well, the first thing to note is that if N equals 0, if nobody buys, then each consumer values the good at 0, and so no one will want to purchase. So part of the demand curve is the vertical line at N equals 0. If everyone expects no one to buy, then no one will buy. Now let's look at the cases where N is positive. Then there will be an indifferent consumer, V bar, who's willing to pay exactly P. Let's call this equation 5.1. Everyone with a V larger than V bar will choose to buy. So the number of people who buy will be 1 minus V bar. We can rearrange this equation to make V bar the subject, and we'll call this equation 5.2. So just as before, we can find our indifferent consumer, V bar. In this case, V bar is equal to P over N, and the number of consumers is 1 minus V bar. Now we want an equation for demand that involves the price and the number of consumers that are purchasing. So we need to take equations 5.1 and 5.2 and eliminate V bar. So by substituting into 5.1 using 5.2, we can get the equation N times V bar, which is 1 minus N, equals P. Or P is equal to N times 1 minus N. So this is the expression for an inverse demand function when N is positive. It tells us how the price is related to the quantity demanded, N. So let's draw this curve. It's a quadratic. We've got N times 1 minus N. When N equals 0, P is 0. When N equals 1, P is also 0. So we have these two horizontal intercepts, and then we'll draw an upside down U shape because the quadratic term here is minus N times N, which is minus N squared. So it has a negative coefficient. So we have horizontal intercepts at n equals 0 and n equals 1. At a half, we have the maximum, and it's equal to a half squared, which is a quarter. So we want to draw a nice smooth quadratic through these points. And this red line here is our demand curve. This part of the demand curve has the equation P equals n times 1 minus n. We also have this vertical portion at 0. Just as with a regular demand curve, the height of the demand curve represents the willingness to pay of the indifferent consumer, the one that's just indifferent between purchasing and not. In contrast to a regular demand curve, this demand curve is not everywhere downward sloping, and for many prices there are multiple quantities that could be demanded. There are multiple equilibria. For prices between 0 and a quarter exclusive, there are 3 possible demands. This is a characteristic of markets with network externalities. There are multiple equilibria. So let's now introduce supply. We are going to assume that this is a perfectly competitive market. All the firms have a constant marginal cost C, and so the supply curve is horizontal at C. What is the equilibrium in this market? Well, for this particular supply curve I've drawn, there are 3 equilibria. There's a low demand equilibrium, there's a middle equilibrium, and there's a high demand equilibrium. Now, the existence of multiple equilibria raises the question of which equilibrium is most likely. To think about this question, we're going to introduce dynamics into this model. This is going to be done in a fairly simple way. We're going to assume that when people are willing to pay more than the cost, then the size of the market expands, and when they're willing to pay less, it contracts. When the demand curve is above the supply curve, we assume the market expands. When the demand curve is below the supply curve, we assume it contracts. So before we look at how this works in the market with network externalities, let's look at how it works in the market without network externalities. So let's draw a supply curve on this diagram. The equilibrium is at the intersection. Now let's see how the dynamics work. If the consumers are willing to pay more than it costs to produce, that is, if the demand curve is above the supply curve, then the market will expand. So if we are to the left of n star, then the market will expand. To the right of n star, the supply curve is above the demand curve, the consumers are willing to pay less than it costs to produce, the market will contract. So you can see the 2 arrows are pointing towards n star. So if we start to the left or the right of the equilibrium n star, we're going to converge towards n star. So this equilibrium point is stable. No matter where we start, we're going to end up there. So let's apply this idea to the market with network externalities. We have these 3 equilibria. If we start between the low and the middle equilibria, then the demand curve is below the supply curve, and so the market will contract. If we start between the middle and the high demand equilibrium, then the demand curve is above the supply curve, and so the market will expand. If we start above the high demand equilibrium, the demand curve is below the supply curve, and so the market will contract. So now let's consider the stability of these 3 equilibria. The middle equilibrium is what's called an unstable equilibrium, because if we start slightly to the left or right of that equilibrium, then we're going to move away from it. So this equilibrium is unstable. The only way to get to the unstable equilibrium is by starting there. On the other hand, if we start between the middle and the low demand equilibrium, then we'll converge to the low demand equilibrium. If we start to the right of the middle equilibrium, then we'll converge to the high demand equilibrium. So as long as we start close enough to the low or the high equilibrium, we're going to converge to them. So the other 2 equilibria are stable. So in this sense, the high demand equilibrium, because it's stable, is more reasonable or more likely than the middle equilibrium. So now let's think about what will happen in this market over time. So over time, it's likely that the cost will be falling. And let's suppose that the number of people connected to the network is perturbed around the equilibrium point 0. This could be the result of business strategies such as initial discounts or promotions, or just the result of people randomly choosing to purchase the product. So if the cost starts, say, at CH, then there's only one equilibrium, no one's going to buy. But as the cost falls, eventually there are equilibria with a positive quantity. But when the cost is at Cm, it takes quite a large perturbation to get over the other side of the demand curve. The increase in quantity has to be enough to get across the demand curve so that we will then converge towards the high equilibrium. As the cost keeps falling, it becomes easier to move across that curve and converge towards the high demand equilibrium. So as the cost of production keeps falling, it becomes more and more likely that these perturbations will tip the market towards the high demand equilibrium. As the cost keeps falling, nothing might happen for a while, but eventually the cost gets low enough that we reach a tipping point and the market is in a disequilibrium. It's between the middle and the high demand equilibrium, and then after some time converges to the high demand equilibrium. So we'll have this increase in sales while the market is in disequilibrium until we get to the high demand equilibrium. So let's see how well this model explains what we see in reality. So here we're looking at the market for fax machines. In the top diagram we have the average price, and in the bottom diagram we have the number of fax machines shipped. We can see in the bottom diagram that the number of fax machines sold was very low until about 1986. We can see in the top diagram that the price for fax machines was quite high until about 1982. And then after that point there's a rapid decrease in the price, and the price then levels out at about 1986. But if we look at the bottom diagram, nothing really happened until 1986. So although the price was falling in this period between 1982 and 1986, we're still in the low demand equilibrium. There's no real increase in the number of fax machines shipped. But eventually, once the prices become low enough, we reach a tipping point, the market is out of equilibrium, and the number of fax machines shipped rises quite rapidly. And then eventually it levels off and we're in the high demand equilibrium. So what happened in this fax machine market fits well with our model. We are in the low equilibrium until the cost and therefore the price falls to a low enough level that it becomes quite likely for the market to tip over that dividing line and move into that area where there's disequilibrium and the quantity is rising rapidly towards the high demand equilibrium. So what are some implications of this model? Well, one is that it may pay to give away or heavily discount the good, at least in the beginning, in order to get past that tipping point. So in goods with network externalities, it makes sense to discount the good because that will increase the number of people buying and then make other people more likely to buy. In markets without network externalities, this effect is not present. So there's not this incentive to give away or heavily discount a good at the beginning. Now, in the case of two-sided markets where a firm receives revenue from both sides, it might be worthwhile to heavily discount one of the goods or even give it away. For example, games consoles are often sold at a loss, at least at the beginning. The PS3, when it came out in 2006, it cost about $805 to produce, and this meant that Sony was making a loss. They were selling the console at a loss of between $225 and $305. In this two-sided market, we have the game producers and the game players. The profit is made from the sales of the games mainly and the accessories and online services. So it makes sense to increase the size of the network by increasing the number of consoles sold to encourage developers to develop games and gamers to buy games and accessories and online services. Another example is with PDF readers. Adobe gives away the PDF reader, And this means that there are lots of people who are able to read PDFs, and therefore it's going to be worthwhile for someone who wants to produce a document to use PDF. And so Adobe can make the money by selling the PDF producers rather than the PDF readers. To summarize, there are lots of goods with network effects. In these markets, there are multiple equilibria, and small changes can tip the market from one equilibrium to another.